Okay, we're going to take a look at the question of arc length. So what are we talking about? In simple terms, if we have a curve, the question is, what is the length of this curve as we travel along it? And so imagine if I were able to sort of take the two ends of this, like if it was a string, and pull it tight, right? What would that length be? If I have a flexible measuring tape, if I went along the curve and measured how long it is, how can I find how long the curve is? And this is a really neat problem. And we're going to proceed using integration. We're going to break up. Let's suppose I'm interested, let's say, what the length is from x equal a to some value x equal b. Okay, so if I go up on the curve, going from that point on the curve to this point on the curve, what's the length going to be? So what are we going to do? Well, what we're going to do is we're going to, like we normally do with integration, we're going to break up our interval into n equally spaced subintervals. I'm going to just do 4 subintervals to illustrate, but break it up into 4 equally spaced subintervals. And remember, our width of each one will keep the same. Delta x, make them equal width. We don't have to, but we're going to do that for ease of notation here. And so what I'm going to do is I'm going to find the value of the function at each of these endpoints of my subintervals. Okay. And to approximate the length of this curve from this point all the way down to this point, what I'm going to simply do is I'm going to take these endpoints of our subintervals, find the value of the function, and just connect the heights of those functions, or height of the function at those two endpoints, and draw that line segment. Now I know how to find the length of a line segment between 2 points, right? Could get that from the Pythagorean Theorem, as we'll see in a minute, and so on. I'll do that for each segment. Now the length of these line segments is not exactly equal to the length of the curve over that subinterval, right? So it's not equal to the length of that curve over that subinterval, but as we go down we get sort of this choppy approximation. But that's our approximation, the length of these line segments. And then what we're going to do, of course, is what we're going to get a better estimate, we're going to create more subintervals, let that delta x get smaller and smaller, get closer and closer together, and hopefully then we will have what in the limit is n, the number of subintervals approaches infinity, we will approach the length of this curve. To sort of motivate the what we're going to get for the integral, I want to focus in on an arbitrary subinterval. I'm going to call it the ith subinterval. So if I have n equally spaced subintervals, let's look at the ith subinterval. So if you remember our notation, that would be from x sub I minus 1 up to x sub I. Remember, we start a as x sub 0, then we have x sub 1, x sub 2, x all the way up to b, which is x sub n. So the first subinterval would be x sub 0 to x sub 1. Second, x sub 1 to x sub 2. So the ith is x sub I minus 1 to x sub I. And let's just suppose the function out on that interval looks like this. There's our function f, whatever it looks like. And again, we'll come up and find these 2 points and the value of the function at these endpoints, go to those heights, and we'll approximate, right, the length of the curve between these 2 points by this red sign. So the length of the curve is this, a little bit longer than the length of this red line, but we're going to approximate that. Now, I'm going to, of course, make use of the Pythagorean theorem here. I'm going to draw a little right triangle right here, and of course this is just our delta x, right, our change in x, which is the difference x sub I minus x sub I minus 1. Here, that's our vertical change, which we can find by what? F of x sub I, the height of this, the height at x sub I that we are in this function, minus f of x sub I minus 1. Right, I'm just going to call that delta y, the change in y. Okay. And so and I'm going to say this is the change in y sub I, because this is the ith subinterval, and these changes in y vary, right, as we move from subinterval to subinterval. Some, the change in y in this first subinterval is not as great as it is in the second subinterval, and so on. So these can change. The delta x's are all the same. These widths are all the same, but this can change. And so then we get our, I'll call this the length, I'll call this delta L sub I, the length of that segment. Okay, so by the Pythagorean theorem, we have a right triangle. The sum of the squares of the two legs equals the square of the hypotenuse, which is the length that we're looking for, really. Let's put those in, plus delta y squared. And so I can solve by taking the square root for this arc, for this length, this approximation to what we call the arc length. Y sub I. Okay, so we get to this point. Now here's the thing. What we are going to make use of is the mean value theorem. If you remember the mean value theorem says on any interval a function that is continuous and differentiable over an interval, then the derivative, or the instantaneous rate of change, if you will, the derivative at one point on this interval will equal the slope of this line, which is the secant line, or the average rate of change of the function. Okay, so at some point, and actually we can even see on this subinterval where that might be, right? Here's below at the bottom of my ruler is this line that we've drawn. If I draw parallel lines, keep moving them until what? Till I just touch the graph of the function f, right about here, right there. That value of x, the derivative, right, the slope of the tangent line, is going to be equal to the slope of the secant line. That's the mean value theorem, and we're going to use that. So the mean value theorem says there exists some point, and I'll call that point that I was talking about. Let's just go ahead and draw that. Got that tangent line right there at that point, coming down about there. That's our, I'll call that C sub I, and that can be anywhere on this. It doesn't really matter where it is. We're guaranteed that it's somewhere in this interval by the mean value theorem. And so by the mean value theorem, we know that there is this C sub I such that f prime evaluated at the slope of this tangent line is equal to the slope of this line. What's the slope of this line? Rise over run, right? Rise is delta yi over run, delta x, right? It's change in the vertical change over the horizontal change, right? That's the average rate of change, the slope of that secant line. Okay, so from this, then I'm going to solve for delta yi by multiplying both sides by delta x. And now I'm going to substitute that in here for delta y sub I. And if I square this thing, I'm going to get f prime of ci squared times delta x squared. All right, so just plug that in, square both these quantities, and we get this. And now I'm going to factor out this delta x squared from both of these. I'm going to factor it out, and of course it's the square root of delta x squared. So what I'm going to get, of course, when I factor out a delta x squared from here, I'm left with 1. Here I'm just left with this f prime of ci squared. Those still under the square root, times what? The square root of delta x squared. Well, that's just delta x. That's just delta x. Okay, so there's our delta Li. Just for that one little segment, there's our approximation. So it involves the derivative of the function. Okay, and so the total length estimate then, or the arc length, if you will, is approximated by the summation I equal 1 to n of these delta Li. So going back up to our I'm going to add each length, choppy length, and then use that as the approximation, right? for I equal 1 to n. So for each arbitrary arc length, we will find an estimate by the length of that line segment. Okay, so what happens then as n goes to infinity for this, right? What do we have here? This is, just take this stuff and stick it in there, right? This is a Riemann sum. This is a Riemann sum. And the limit as n goes to infinity is going to be the definite integral. And that's what we have down here, right? As n goes to infinity, we come up with this formula for what we call the arc length of the curve from a to b here, right? Notice the integral is going to go from a to b. And you can see this becomes the integral. And of course, the c sub I now, we're just going to say, f prime of x, all right? Because these subintervals as n goes to infinity, these crunch down together to 1 point, or approaching one point. Right? The delta x is getting smaller and smaller and smaller as n gets bigger and bigger and bigger. We get more and more subintervals, right? And the idea then is, in that limit process, we reach the definite integral. Okay. There are some conditions on the function, right? The derivative needs to be continuous. We've got to be careful about that. The function that we're integrating is what we call a smooth function. And so those are the types that we will be looking at. So let's just apply this. This is the arc length now. One thing I'll just say about this, we're going to look at some fairly contrived examples, because this integral here in general, if you just pick an arbitrary function and plug it in here and you try and find the antiderivative, well, good luck. It's either going to be very, very difficult or impossible. Of course, in the impossible case, we don't say we give up. We can do what? We can use a numerical method to approximate, right, the integral. We can use what we've learned before about trapezoid rule, Simpson's rule, and so on. So we can use a numerical method to estimate the arc length of the curve. But we're going to do some examples where we can actually do the integration. So let's start off with our first example here. Keep that formula up at the top. Let's find the arc length of the graph of the function y equals the natural log of cosine of x over this interval. Kind of interesting thing. Here's the portion of the curve that I've drawn. And it's helpful to look at the curve. You might want to even, sort of estimate what would the length of this curve be. You can sort of estimate it by finding the distance between the points here. So 0, 0 is right here. And then pi over 4, that's about 3/4, a little more than 3/4, so somewhere over in here, I don't know. Pi over 4 is right about here. A little bit more than 3/4 actually, right? 3.14 divided by 4. And you could find the length of the line segment connecting these 2 points, right? You can estimate, you can find that pretty easy. And that that would be a little bit less than the actual arc length. That would be a little less than the actual arc length. Okay, so here we've got f prime of x. Of course, if I let y be the function f of x, then we have y prime is f prime of x, right? So I'm going to use y prime here. So what is y prime in this case? Y is this function. Well, I've got chain rule, right? I've got chain rule. So let's say y is equal to, in this case, the natural log of cosine of x, and so this is chain rule. Outer function is the natural log, inner function is cosine of x. So the derivative of the outer function, natural log of u, is what? 1 over u, right? Derivative of natural log of u is 1 over u, so that's 1 over cosine of x times what? The derivative of the inner function, which is cosine of x. Of course, the derivative of cosine of x is negative sine of x. So negative sine of x times cosine of x is what? Negative sine x divided by cosine x. Does that look familiar? Can we write that a little more compactly? Yeah, this is just negative sine divided by cosine, negative tangent x. Okay. So what is this arc length? Let's look at our formula up there, right? We're going to use this. The arc length L is from A to B. What is x going from? A is 0, B is pi over 4. Square root of 1 plus f prime of x, or in this case y prime squared. So if I square negative tangent x, what do I get? Positive tangent squared x. Now you look at this and say, well, what are we going to do? I don't know. Well, this should look kind of familiar from what when we were doing trig substitution. At least this right here, whoops, should look familiar. What is 1 plus tangent squared x? What's 1 plus tangent squared? By the Pythagorean identity, right, we've used before, that's secant squared x, right? 1 plus tangent squared x is secant squared x. And so when I take the square root of secant squared x, I get just secant x. And so this function actually simplifies down to this. And what is the antiderivative of secant x? Well, we've learned that. That is the natural log of the absolute value of secant x plus tangent x. And we're evaluating that at pi over 4 and at 0. So there's the evaluation at pi over 4 minus the evaluation at 0. Cosine of pi over 4 is 1 divided by the square root of 2, or the square root of 2 over 2. So secant of pi over 4 is the reciprocal of 1 divided by the square root of 2, or just square root of 2. Tangent of pi over 4, right, is 1, right, since sine and cosine of pi over 4 are both equal to the square root of 2 over 2. Tangent of pi over 4 is 1. Cosine of 0 is 1, so the reciprocal of 1, which is secant of 0, is also 1. Tangent of 0 is 0, right? Sine over cosine. Sine of 0 is 0. Cosine of 0 is 1. 0 divided by 1 is 0. So you should be able to get these values from the unit circle. But now we're set to see what we have. Square root of 2 plus 1. We take the natural log of that. And notice square root of 2 and 1 are both positive. So the absolute value of positive number is just that positive number. I'm going to get rid of the absolute values there. Minus the natural log of what? 1 plus 0. Absolute value of 1 is 1. Natural log of 1. But the natural log of 1 is indeed 0. And so we get the exact length of this curve, right? Which you can approximate. If you were wanting to check, that might be a good reason. This is about 0.88, but there's the actual arc length you want to give. But this is the actual length. Does that seem reasonable, about 0.88? I mean, it does seem reasonable here. Again, you might want to compute what the actual length is of this line segment to compare, but it certainly seems reasonable. If I got an answer like 88, well, clearly this distance, looking at this scale, this is not 88 units long, this curve. Okay, so this curve, the length of this curve, is given by this expression. Okay, let's look at one more example. Another sort of contrived example. This is the graph, or this is the function y equal x minus 1 to the 3/2 power between 1 comma 0 and 5 comma 8. So I've graphed that function here. So 1 comma 0 is right there, to 5 comma 8 right up there. So what's the length of that? And again, you can use find the distance between these 2 points just to give you some reference to see if your answer is reasonable. So we're going to look at the derivative y prime. Again, I've got a chain rule, right? The outer function is u to the 3/2, inner function x minus 1. So I do 3/2 times, or 3/2 x minus 1 to what? 3/2 minus 1 power is 1/2. So bring the power down, subtract 1. And then times what? The derivative of the inner function, but the derivative of x minus 1, that is just equal to 1. Okay. So I'm now going to square y prime. If I square 3/2, I get 9/4. If I square x minus 1 to the 1/2, I multiply exponents. A half times 2 is 1. I just get x minus 1. Now I'm going to go ahead and write this out, distributing that 9/4 as 9/4 x minus 9/4. Okay. So my arc length, and again, let me pull that. Let's look at that formula here that we have for arc length, right? Our arc length is from A to B. So what is A? We're going from 1 to 5. and it's the square root of 1 plus 9/4 x minus 9/4. So I've already squared y prime right here. That's 9/4 x minus 9. There's y prime squared. 1 plus that. Now 1 minus 9/4 is 4/4 minus 9/4. 4/4 minus 9/4 is negative 5/4. So let me just simplify that first. (4/4 minus 9/4 is negative 5/4. Now I'm going to do a substitution here. So under the radical, I'm going to let that be my u. That's kind of weird. Why do I have a couple equal signs in there? Well, I don't know. Okay, this is okay. So let's let u be what? What's under the radical? So du is what? 9/4 dx. All I have is a dx, so I'm going to multiply both sides by 4/9. So I get 4/9 du is dx. I also want to change the limits in this case because I have a definite integral. So when x is 1, what is u? I plug in x is 1 here. I get 9/4 minus 5/4, which is 4/4, which is 1. Well, hey, that doesn't change. X is 1, u is 1. But, however, if x is 5, I get what? U is 9 times 5. Let's say 45/4, right? 9 times 5 is 45/4 minus 5/4. 45 minus 5 is 40. 40/4 is 10. So from 5, I go to 10. So with this, my integral becomes from 1 to 5, now goes from 1 to 10. And I've got the square root of u, which is u to the 1/2, right? Square root of u, right? What u to the 1/2. And what's my dx? 4/9 du. So that 4/9 I'm going to pull out. I've got 4/9 du. So now the integral is is doable, right? That's the whole point of substitution. The antiderivative of u to the 1/2 is what? Add 1 to 1/2, which is 3/2. Divided by 3/2 is the same as multiplying by 2/3. And we're going from 1 to 10. I can do what I got here, 8/27 if I multiply that by 8/27. And then what do I have? 10 to the 3/2 power minus 1 to the 3/2 power, which is just 1. Okay, and that's about as good as I can go because I don't know what the square root of 10 is. Square root of 10 is not a perfect 10 is not a perfect square, but I can approximate this again. This is about 9.07. And again, you should probably do that. Here's the exact answer for the arc length of that curve, but here is the estimate. And so you can see, does that seem reasonable that that's about 9 units from here to here along, going along this curve? And that seems reasonable. That seems reasonable. Okay, so a couple examples, very contrived. Again, we're going to do one in the next video that's a little more challenging, requires a little bit of algebra to manipulate to get it to something we can find the antiderivative of. So we'll do that, as well as look at surface area for a solid of revolution. So we'll look at that interesting problem in the next video.